kind of convinced that how important it is to do research in the neutrinos, neutrino physics. You also are convinced that how difficult it is to do research or experiment, detect the neutrinos. Now the question is, how do we go about doing it, and who is going to kind of do this at the forefront of, let us say, the science and technology that we talk about. The tagline of the Indian Science Congress itself is science and technology for national development. So how in some way the building of INO experiment in this country by using completely indigenous technology is also something which coincides with the tagline of this very congress that we are going to hold here. I also want to make one observation. Unlike many of the basic science experiments which we do in material science or other fields, necessarily the detectors, when you do the experiments with high energy physics or nuclear physics, the entire process of building the detectors or detecting the, for detecting any of the particles that you are talking about has to be done indigenously, and it has to be done using materials which are very cheap, because you typically require very large number of detector channels. Okay. So with that, when you start about the INO project, as you kind of know, the primary goal of INO project is neutrino physics, but the INO project actually includes construction of the large cavern, underground cavern, and also the associated surface facilities, and the construction of the ICAL detector that you heard about. And what is also more important is setting up the Interinstitutional Center for High Energy Physics. Now, in the process of doing this major project, a successful INO industry and interface has developed, because, as I said before, it is a large scale experimental science activity. Now, it goes without saying that most of the jobs that are done in typically high energy physics is done by students. Then it is important to also train for human resource development for this country, that we had this INO graduate training program under the umbrella of Homi Bhabha National Institute, or HBNI, and we are in the 9th year of its operation this year. Now, starting from the underground tunnel, which is quite huge, in fact it is probably much bigger than a large metro station that you can talk about, but more importantly it is built at much higher depth of the order of about 1.5 kilometers. Now, you heard about various technical details of this project, and the entire project has been kind of studied in detail, and a very detailed report has been given by Tamil Nadu Generation and Distribution Company Corporation Limited, or we also call as Tamil Nadu Electricity Board, right. And this is with their help that we are able to conceive such a big underground tunnel and how to go about building it. Now, as you also heard about this gigantic detector which weighs about 50,000 tons, but again requires a large collaboration between the research institutes and the industry. And what is shown on this slide on the right side, you can kind of see that the Tata Consultancy engineer along with a large number of industries, local industries who are experts in machining, fabrication and structural engineering is involved with this. If you look at this detector itself, it consists of large number of iron plates, as you see on the right side, which are about each being about 4 tons, about 4 meter by 2 meter in dimension. And also on the left, you can actually see there are several other very large mechanical components. One that you see on either side of this blue path is what is a kind of a trolley which is used for servicing the detector. Just to give you a perspective, you can see the how big this gigantic detector is, about height of about 4-storied building, right. Now, as I said, now I would like to also go a little bit into each of these components that I talk about. The first thing that comes is we are going to build this detector using iron plates. Iron plates come with such kind of a large sheets, each weighing about 4 ton, and we are thankful there is a large presence of steel industry in this country, SR Steel, the Steel Authority of India Limited, Jindal Steel, and other industries who are main partners into building, providing a very high quality so-called low carbon steel. This is a special steel that requires, which will enable us to kind of magnetize this entire detector to about 1.5 Tesla. So we have this capability of producing such steel locally, and once you have the steel plates, you also have to magnetize, because you want to distinguish the charges of muons. And then the magnetic coil, of course, is important, because we do not have that kind of expertise to produce this so-called oil oxygen free copper. But all the entire engineering, if you look at it, how you braze these copper coils, how you bend with a large, this each one is something like about 15 or 16 meters long. Now, all these technologies again we are able to garner support and we are able to catalyze the local industry to do this job for us. And when the detector completely comes up, the magnet part of it, the coil part of it is what is shown on the lower right corner, right. Now, I also mentioned about this very large 15-meter tall kind of trolley which is able to move in and around the detector, but at the precision of few millimeters is what is shown in a picture on the left side, but it is now a reality thanks to a large number of industries which are, some of them are based in Vellore and Coimbatore and so on, and the basic design actually is again done by Tata Consulting Engineer. Every aspect of this goes by conceiving the design, the need by the collaboration group, and we approach an industry and we work not like a, not like as if you order a component to an industry, but we are actually equal partners there. Just to scare you with numbers what ICAL is made of, you can really look at it, some of those numbers that are already shown before and some are shown here. Even if you forget about rest of the whole thing, you are talking about the large number of resistive plate detectors. These are the basic detector elements that ICAL is going to made of, the active detectors. You are going to kind of use about 30,000 of them, which will cover something like 16 soccer fields, it's about 100,000 square meters. And if you talk about reading this data from the detectors, you require almost about 4 million detector channels, right. Compare this with a typical ECG machine which will actually host about 10 to 12 channels. So, these are some of the challenges that we need to kind of meet before the neutrinos could be kind of detected and the rest of the physics can be done. Just to give you one couple of lines about the basic detector itself is very simple. It's made of two parallel glass plates or backlight plates and filled with gas of special mixture. There are, if you see on the top and bottom, there are the so-called pickup panels which are going to pick up very tiny signals whenever a charged particle basically passes through. So, each of these components again, as I said, has to be built from very low cost materials, and then they are going to be mass produced in the industry, right. This is very important. Now, if you are still not convinced what this project is about, what this detector building is about, look at this table which lists all the RPC detectors that are being employed in this world right now from the top to bottom. If you look at the just the third column, that kind of tells, second column, that tells you what is the typical area of these detectors that are actually used in many major projects. So, look at the last column, it tells you that you are talking about 100,000 meters square of RPC deployment area, which even if is much larger than the sum total of all those detectors. And all these have to be built from very inexpensive materials, and it has to be more importantly built in this country. You can't just import like a component that you typically do it in other cases. So, you start from because the basic electrode material is glass. So, you have to approach glass industries. On the left you can see two major glass industries. We work with them in tandem to kind of bring a very special glass that is required to build this kind of detectors. Not special in terms of the construction, but you require a very large area. Then one of the challenge that comes to apply a field across these plates is so called, you apply on across kind of paint that is painted on either side of the RPC gas gap. So, you have to build a technique. You can't obviously do like by hand the way you do a car painting, etc. And see on the left there is a machine, automated machine which is built in order to do this. Now, you approach a car painting company because those are people who will have expertise on this, and you can see on the right the entire system including the control system that was developed by Walchand Industries and a company, car coating company on the right side. Then, but when you talk about, it's not just about only looking at one technique, we also look at painting not just because of spray, also using what is more well proven technique called screen printing. You see four quadrants, four pictures of how typically the screen printing is done in the case of glass. This is done industrially in a company called Saint Gobain, which is very close to Chennai, located in a place called Sri Perumbudur. Okay, all these processes, the entire optimization of how exactly you want to do, what is the parameters that you get about, is actually done with a very close interaction with us. The way we do it is actually our people being there and train the industry, and then then they proceed further. Now, that's not enough. If you want to place 2 meter by 2 meter glasses along, then you require some kind of a spacers between them, but who will give you very precise spacers of 2 millimeters. They are not produced. So, you have to actually conceive, design, approach a plastic company who will do extrusions or molding kind of thing and produce those components what are kind of shown on the left. Now, please keep reading those company names that are given there. So, you will typically see that we already are in collaboration with more than 100 companies to do work for us, and we work for them and vice versa. So, that is the kind of interface that we are talking about. When you want to build 30,000 of glasses, typically students cannot kind of build this. So you have to build robots who will actually do these things rather automatically. You see one such robot that is shown here, which is built by a company from Coimbatore, which is able to kind of do the entire process of building such kind of RPC detectors, and that is how you will be able to build, let us say, about 30,000 of them in about 2 or 3 years, right. So that is the automatic gap making. Now the signal that is picked up, again, it looks a very simple way to look at, this as a panels which are placed basically a plastic material in the middle and padded on either side by a copper or aluminum panels, but these materials never exist in these industries. So you have to convince them, you have to train them, you have to design them and get them produced in a large number. You require something like 250,000 meter square of these pickup panels. So this cannot be just done or ordered the way you do a typical let us say scientific equipment, right. And look at all these industries that are listed on this plot, right, on the view graph here. And as it was mentioned, these RPC detectors use a very special mixture of gas. Again, these are not off the shelf components. You can't go and say, please give me a gas system to be used in ICAL detectors. So you have to actually start designing the system, and because the gas that you use is very expensive, you don't want to let the gas go into the atmosphere. Of course, it's also a cause concern, right. So therefore, you have to, starting from a very simple system that you see on the left side, you go and build a very, very sophisticated system which picks up the gas which is coming out of the RPC detector and flows back into the loop. So therefore, there is no chance of gas getting released into the atmosphere at all. And you see the kind of volume of gas that each of these detectors will hold, that is something like 200,000 liters square of gas at any given point of time. So you have to handle carefully those developments, right. And now for holding the RPC detectors, you require a kind of special tray, that is also something which you have to build using either a fiberglass or you have to use a carbon film laminated. This is again an industry based in Pune, whose help we are able to build and mass produce these trays. Okay. When it comes to electronics, the information that you want, as it was shown by earlier speaker, is how the particles actually go and track through the detector, right. And also you want to precisely measure the timing of these particles passing through to a level of about 200 picoseconds. You see on the left side a large number of detector functional modules that needs to be built. This is a big challenge, because for electronics engineers, when you want to talk about building about 4 million detector channels, we don't even go and buy components or ICs, integrated circuits in the market, because those ICs or integrated circuits or ASICs are not available for your application. You don't find an IC which will work at 200 picosecond time resolution. So you end up actually building these chips by yourself and produce them by yourself. There are foundries, unfortunately not so many in the country, but you go out and actually produce them, but the entire design, characterization, everything is done. You see on the left, they are produced by the Bharat Electronics Limited, called hybrid microcircuits, and in the middle you have what is called application specific integrated circuits. This is a very, very challenging area for engineers particularly to design such kind of state of the art kind of chips. And on the right you see these timing devices which measure the relativistic particles passing through the detector at a resolution of about 200 picoseconds. These are all designed and produced by us, by the collaboration. And of course, all of these ICs, integrated circuits, have large applications outside this experiment. So that is the big spin-off that you actually see this thing. Now what about boards? You require something like 600,000 types of boards that will read the signal from this detector. Okay, just imagine how many boards you would have seen in a PC, in your cell phone, or all your labs put together. Who will build all this? The students, the engineers design these boards. They are of course manufactured outside. Look at this number of companies that we are engaged with, and these really pushed the technology limits of manufacturing technologies, right. Now just coming on to the other flip side, as I said, I mentioned that most of the work is done by students. Okay, now how do you take the students? Of course we go through a national entrance exam that is done by TIFR, and based on the score of the students, we actually call students for an interview, and we pick them up and give them a training in the experimental areas for about a year, followed by doing a research program next 4 or 5 years with their thesis, guide, and so on. This is how the PhD program, INO graduate training program works. As I told you, it is already in the 9th year of its operation, and the program started in 2008, and main emphasis, as I said, is on the experimental techniques and detector and instrumentation development. Of course, scientific human resource development for future nuclear and high energy physics detectors is a main idea of why we have such kind of program. On the right, you can actually see roughly the kind of syllabus or the curriculum that we kind of have. We already have trained, and there are about more than 30 students who have been trained. Some of them have already obtained their PhD, and they are doing very well already in various international labs, and they have extensive and very specially designed outreach programs and experiments not only for PhD students, but lot of other students come and get trained in our institute, okay. Helping the institutes to set up high energy physics detector and instrumentation courses is also one of our main ideas of the scientific program. So with that I come to the summary. I want to say the INO project with all its unprecedented scale and reach has succeeded in fostering technologies between partnership between local industry and research community, and it is providing of course Indian students with a training and ground for their skills development in modern experimental physics. Therefore, the local industries and the students are not just the beneficiaries of this project, but we consider them as actually equal partners or the stakeholders. So the project has already started creating an ecosystem of a mega science laboratory anywhere comparable to anywhere in the world, that the local industries and students can only now leverage on and then grow. So as I said, the tagline of ISE, the tagline of INO, I think turns out to be the same: science and technology for national development. Thank you very much.